Today the topic of discussion is B tree, and in B tree we'll see a deletion of node, that is deletion of key from leaf node and deletion of key from internal node. So we have already discussed how to delete a key from leaf node. So if you are directly coming to this video, then I request you to kindly watch the video number 1 of deletion, which was deleting keys from leaf node, which we have already discussed. The reason behind making 2 videos is that because video is taking some longer time, because there are so much concept which I need to explain. So it took near about 18 minutes for me to explain the first topic, which is deleting a key from leaf node. Now we'll see the second part, deleting a key from internal node. So I request you, if you are directly coming to watch this video, kindly watch the first part of deletion. Fine. So let's start the case. So as I already told you that there are 2 cases in deletion. If a target key is in leaf node, that is if the key you want to delete is in leaf node, we have already discussed, and today we'll discuss if the target key is in internal node. Which are internal node? These are internal node, that is if you want to delete any element, suppose 91 or 71 or 81 from non-leaf nodes. So what this tree is? This tree is obtained after deleting keys from leaf nodes. Fine. So I request you to kindly watch the video, and in last part of that video, in minutes of that video, you will find that we have finally derived this tree after deleting keys from leaf node. Now in the given tree, that is in the intermediate tree, we'll use which concept? We'll use the concept above concept. Which concept? This concept B concept, that if the target key is in the internal node, that is the keys you want to delete is not in leaf node. Now second part. As I already told you that the order of given tree is M. The order of given tree is M, which is 5. So if the order is 5, then what is the use of order and why we are using order? So let me explain you one thing. In case of deletion, we take minimum number of element. In case of insertion, we take maximum number of element, because if you are inserting in a node, then there is a limit. There is always a upper bound. If I ask you to remember those properties of B tree, that there is always a upper bound and lower bound. That is maximum element can a node have, or minimum number of element a node can have. So since we are deleting, so we are reducing element, so there should be some limit that how much we can reduce, how much we can delete. So minimum number of key in a root node can be 1. That is, a root can have 1 key. That is, a root can have 1 key. But if the node is not root, then how many minimum number of key it is required? That minimum number of key in any node other than root is, formula is ceiling of M by 2 minus 1. What is M? 5 given. 5 by 2 is 2.5. Ceiling is 3. 3 minus 1 become 2. So finally, what is 2? That is any node other than root. Any node other than root must have 2 keys. Any node other than root must have 2 keys. That is, you cannot delete a node. You cannot delete a key if a node is having only two keys. No, that is 2 is the minimum value. You cannot go beyond that. Fine. Okay. So I'll not discuss the maximum case, because in case of deletion, we always discuss minimum case. We have already discussed the maximum case in insertion. So let's start with second part, that is case 2. So here we'll discuss the case 2. If the target key is non-leaf node, that is, we are targeting to delete a key from non-leaf node. So let's draw this diagram. So let me draw the diagram first. Okay, so we have drawn a tree which was intermediate part of tree which we obtained after deleting keys from leaf node. Now we'll delete keys from non-leaf node, that is from here, or from here. So let's start with deletion. Fine. Okay, let's start with deletion. So let me change the color of my pen so that things get easily visible to you. Let's start. So now suppose we are discussing the second case, and if we want to delete element 71. So where is 71? I'll not search 71, because search 71 is less than, so you will come here and then you will search here. So this is 71. Suppose now you have to delete 71. So how 71 will be deleted? Because 71 is the internal node. The method is, if 71 needs to be deleted, then this place will be overtaken by either its in order successor or its in order predecessor. So deletion, I'm writing deletion. So first element which I need to delete is 71. So if 71 needs to be deleted, then this place will be taken by either its in order predecessor or its pre-order successor. So if I see what is in order predecessor, the left node of 71, the maximum element of left node of 71 will be the predecessor. So 69 will be the predecessor, and the minimum node, minimum key of right node will be the in order successor. So can I replace 74 with 71? No, because this will say sorry, because this node has minimum number of element, because minimum number of element we have just discussed is 2. Any node except root cannot have less than 2 element. So if 74 will go, then who will no, 76 will be only one element. So this will say sorry. So this node will, this 71 will ask from its left child, can you give me your in order successor? Can you give me my in order successor? This node will say yes, because I have more than 2 number of keys. So what will happen? 69 will come here. Fine. So 69 will come here. I'm making it more clear then. 69 will take place, and 69 will delete from this place. Fine. So 69 will go up, and finally this will be the structure. So finally this will be the structure where what happened, where actually what happened, that 70 where what happened, we have deleted 71 and 69 which was in order. So in case of 71, who took its proposition? It's in order predecessor. So this is first case. Now suppose you want to delete 96. So where is 96? Let me check 96. This is 96. This is 96. So can I delete 96? So I have to check. Can he ask from its left node? No, left node will say sorry, because it's already no. This cannot be replaced by its in order predecessor. Can it be replaced by its in order successor? Yes, because in order successor will be the minimum element, and this node has more than 2 number of keys. So what will happen? This 96 will get deleted. 101 will come up. Fine. And this 101 will be deleted from this place. Fine. This 101 will be deleted. Fine. So finally I deleted two things, that is 71 and 101. So how 101 deleted? From in order successor, from in order successor. So hope these two cases are clear. Now you might be thinking, what if the node is, we are deleting either in order successor or the node having in order predecessor, though both the node do not have more than minimum number of element. What will happen? So let's discuss that case also. So third case will be delete 78. So if we want to delete 78, so what is in order successor of 78? So in order successor of 78 is 79, and in order predecessor of 78 is 76. Both the node will say sorry. Sorry, we cannot help you. Why? Because we both are having less than minimum, we both are having minimum number of elements. In that case, what will happen? These two node will get merged. And what will happen? This two node will get merged, and this 78 will get deleted. So 78, so when we were deleting 78, this is the case of merge. So I'm writing merge. Why? Because both in order successor and the node having in order predecessor, both are helpless to help. Fine. So we'll merge them. So if we'll merge them, what will happen? So let me merge them. So if we'll merge them, what will happen? 74, 76, 79 and 80 will come, will take one place. Fine, we have finally merged, and this 78 will get deleted. So when this 78 get deleted, okay, so what will happen? The 69 will remain, that is the node will have only 11, 51 and 69, and now there are 3 keys, and so child are 4. So again, it's a B tree. There is no issue of violation. Fine. Okay, now what to do? Now your job, as we have discussed 3 cases, that is case 1, this is case 2, and this one is case 3. Now we'll discuss another things also. Now if we want to delete 81 root node, that is, we want to delete root node. what will happen if we want to delete, root node, then what will happen? Fine. So we want to delete root node 81. So you know that when this element get deleted, no, so it will ask with whom? It will ask from either its in order successor or its in order predecessor. So what will be the in order predecessor of this node? So the entire left subtree, the entire in entire left subtree, I should use like this, in entire left subtree, the maximum element in entire left subtree, the maximum element will be its in order predecessor. So which is the maximum element? 18. So this is its in order predecessor, or it can also be replaced by its in order successor. What is in order successor of this node? The minimum element of its entire right subtree. The minimum element of entire subtree is this is in order successor. Now if you see in order predecessor node and if you see in order successor node, both are capable of donating. Why? Because they both has more than minimum number of elements. So let's take any node. So let's choose this in order predecessor. So if we have chosen this in order predecessor, fine. So let me delete all this rubbish. This rubbish. So see this. Let me delete all this rubbish then. Okay. I'm so sorry. So let me delete all this rubbish. So what will, suppose I'm replacing 81. So 81 is deleted. So when 81 is deleted, who will take this position? 80 will come. Fine. And this 80 will get deleted from this node. So now this will be the final structure after the deletion of root node. So everything is fine. Fine. Okay. Now what happens? So we have finally deleted 80, and what happened? That 80 took place. Okay, finally 80 took place. Now next which what we want to delete is suppose we want to delete. Let me delete. Let me delete. We have deleted root node. Okay, now we want to delete 101. So suppose if you want to delete 101, so what will happen? So this 101 will be the case, again the same case. Neither its in order predecessor node nor its in order successor node, both are helpless. Both will say sorry, we cannot help you. We cannot give you any element. If you want to go, you go, or we cannot give you element. So in that case, what we do, we use this merge method. No, case third. So in that case, we'll merge. So what will happen finally? So when we'll merge, so what will happen? Let me merge them. Okay, so what will happen? 111 will come here, 112 will come here. So finally I'll merge this node. I'll delete all this rubbish now. So it's creating and this 101 get deleted. Fine, this 101 get deleted. So now this node has only element 91, and since there is one element, there is two child. Is there any kind of mistake? Yes, there is still something pending. So I'm writing, when you're deleting 101, something still is pending. What is pending? This 91 is violating which rule? This rule, that is, any node other than root cannot have less than two number of keys. So this node is having only one key. So this is violating the rule. So if this is violating the rule, then what is the case? So 91, now 91 will ask its sibling. Who is the sibling of 91? This. So it will ask its sibling, hello sibling. Sibling will say hello. So this will say, can you please borrow me? Can you please help me with one of your element, because you have more than one element, more than minimum number of elements. So this node will say, yes, I can help. So what happens? So what we have explained, how this helping will take place. First of all, what will happen? This 69 will go up and 80 will come down. So this will take place. So what will happen? This 16, the moment this 69 will go up, so 69 will come here. Fine. And what will happen? 80 will come down. So when 80 will come down, 80 will come first, and 91 will come here. Fine. So 91 will come here, 80 will go down and 91 will come here. Now what happens? So is this tree is okay? No, now because this node has only 2 elements, and how it can attain 4 child? Because our child less than 11 will come here, 11 and 51 will come here, greater than 51 will come here. How this will be accommodated? So finally this link will get broken. This link will get broken. Fine. And what will happen? This link will get attached here. Fine. So these are elements which are less than 80. So this link will come here. These are elements which are between 80 and 91, and this link will start from this place. Finally what happens? So when you are deleting 101, so there are 2 more cases of deletion taking place, and finally some structure will take place. Finally, if you see the structure, again it's a B tree. That no node is having less than 2 keys, and if there are 2 keys there are 3 children. If there are 2 keys there are 3 children. Fine. And all of them are increasing order. So fine, till now everything remains same, and it's fantastic. Now we'll discuss one more case which is very important. So we'll discuss last case, which is shrinking of height. So the last case, I'll use LC. Last case is shrinking, shrinking, shrinking of height, height. So height of shrinking of height. Fine. So we'll discuss shrinking of height. So what is the shrinking of height is? So let's start. So let me rub this. So let's delete. Now we have to delete. Now I'm taking both the cases. So in shrinking of height, both the cases are coming. Now we'll include both the cases. Case 1. Now we'll include both the cases. That is leaf node deletion plus non-leaf node deletion. No, leaf node deletion and leaf node deletion plus non-leaf node deletion. We'll discuss both the cases now. So in shrinking we'll discuss both the cases. Hope you remember now both the cases. So we'll start from both the cases. So first of all, delete. If you want to delete 7, where is 7? 7 is here. 7 is in leaf node. And leaf node having more than minimum number of element. Can we delete? Yes, simply delete. No issue. I've already explained you. I'm not going to explain now. Simply delete. I've deleted. So simply delete it. Fine. Now comes 28 to delete. Can I delete 28? Yes, delete, because 28 is here and this node is having more than minimum number of element. Delete 28. Simply delete. Yes, we have deleted. Now the case comes 61. Delete 61. Can we delete 61? Yes, delete. No issue. You can delete because this node has more than minimum number of element. Deleted. 61 deleted. Finally deleted. No issue. Then you were asked to delete 17. Can we delete 17? Yes, delete. No issue. You can delete. Fine, because this node has more than minimum number of elements. So 17 deleted. Now till now everything remained fine. It was looking very fantastic. Now see what happened when one element were asked to delete, and that element is 51. Suppose now the game changes. Now 51 is asked to delete. So if 51, what is 51? Internal case 2. No, this is the case 2 deletion. So case 2 deletion, that is we are deleting a key from internal node. So if 51 needs to delete, then who will take this position? Either it's in order successor, this will say sorry, I cannot help you. Either it's in order successor, this node will say sorry, I cannot help you. Why? Because they both are less than, they both are equal to minimum. So they both are already minimum. So what will happen? Merge, you know. So what will happen? So when will merge? So 52 will come here and 53 will come here, and this both node get merged. So I'll delete this node and 51 will get deleted. So finally what happens? Here you have one element 11. This is less than 11 and this is greater than 11. Is it fine? No, still something is pending. What is pending? This is violating. This node is violating. Why violating? Because violating, this node is having not minimum number of elements, because this is internal node other than root. This is not root, and any node other than root cannot have less than 2 number of keys. So since this node is having less than 2 number of keys, so what will happen? 11 will ask its sibling, hello sibling. Sibling will say hello. He will say, can you please borrow me? Can you please borrow? Can you please give me one of your element so that I feel comfortable? So this, what this sibling will say now? Sorry, I cannot help you because I I am already having less number of elements. So what will happen? Either neither it's no, nobody is ready to help 11. So where this 11 will go? 11 will go to the God. Who is God? Root node. 11 will say, God, please help me. So God will say, there is only one option, merge. There is only one option, merge. So we'll finally merge. So when we'll merge, then 11 will come, 69 will come, 80 will come, and 91 will come. So this node will get merged. Finally, nodes are getting merged. So what are 11 less than 11? So let me write what are less than 11? 5 and 6. Fine. So this will come to one part. Then what are greater than 15, 16? 15, 16, and then we have 52, and then we have 53. So this will come here. Fine. This will come here. Okay, then what are greater than 69? This, and less than 80. So here what will happen? 74, 76, 79. Fine. What about this 80 and 91? What something which is greater than 80 and less than 91 is 82, 83 and 90. 82, 83 and 90. Fine. Okay, so this will come here. And what about this? 91 says 93, 94, 111 and 112. Finally, you have achieved a B tree. This is the final B tree, which is less in height. Fine. So height has shrinked. Height has shrinked. The height of this was 2, but the height of this is only 1. Fine. So the height is shrinked just because of deleting what? One thus because of deleting 51. So see, you have seen that 51, on deleting 51, the entire height of this B tree got shrinked. So this was the final deletion case of non-leaf node. So at last I'll say